Okay, so in this video, what we're going to do is we're going to find the sum of the first n odd numbers, all right? And the way we're going to do is by using the concept of arithmetic progressions, or AP. So what is an arithmetic progression? Well, if you don't know what that is, refer to my earlier videos, and you'll figure out that it actually is just any sequence in which the difference between any two consecutive numbers is a constant. So what we have here is a sort of AP. I mean, it's precisely an AP, but the way we should have gone about it is by asking ourselves the question whether or not this can be represented as an AP or not. And we can check that it can be, in fact, because if you take any two consecutive numbers, say if I take 3 and 5, the difference between 3 and 5 is going to be 2. Similarly, between 5 and 7, it's 2 again. And 7 and 9, that's 2 again. You do this with any two consecutive odd numbers, and you would find that the difference is, in fact, 2, right? Because there's one 8 that is hidden here, or the other way to think is that you have an odd, and an even number there. So the difference is 1 and 2, right? So that's another way to think of it. Okay, so this clearly has a common difference, or what we like to call as D, to be 2, right? Now, what can we say about the first term? The first term here is the first term of the AP, which is just by observation, it's just 1. So A sub 1 is 1, right? Now, if we have the first term and the common difference, we can write any term of an AP, right? So let's check whether A sub n is precisely what it should be. So A sub n would be, using the formula for AP, would be, well, A1 plus n minus 1 times D. And you fit in the values for A1, and that is just 1, and n minus 1 times 2. Do the math, this is just 2n minus 1. Okay, so a pretty okay expression, I would say, right? That is the nth term. So we can clearly make a quick check whether or not this actually fits. And we would notice that if we put n to be, say, 1, then an would be just 2 into 1 minus 1. That would be 2 into 1 minus 1 will be just 1. So a1 is clearly 1. So that makes sense. You want to do, say, let's figure out the third odd number. It should be the first, second, third. Well, the third should be 5, the fourth should be 7. So let's calculate, say, a sub 3, okay? And that should be 2 times 3 minus 1. Well, that turns out to be 2 into 3 is 6, minus 1, that is 5. And that clearly is 5. So this matches as well. So this clearly, the series has been represented by this expression starting from n equal to 1 going all the way till n. So that's one way to think of it. Now that we have this all stated, what we can do is we can basically go on and use the sum formula to actually figure out this sum of this expression. Okay, so I'm writing this again here. So 1 plus 3 plus 5, so on and so forth. The nth term would be 2n minus 1. Okay, so that's how we're going to write this sum. Now the sum would be nothing but n by 2. Remember the formula: 2a, the first term, 2a, or a sub 1, well, that is 1, plus n minus 1 times the common difference, well, that is 2. Okay, so if you do the math, that is n by 2, 2 plus 2n minus 2. What we can do here is we can clearly just get rid of these terms because 2 minus 2 is 0, and we're left with n by 2 times 2n. Cancel the 2's out, and you're left with n squared. Well, that's a very neat expression. So what we have really found out is that if we add n odd numbers, we actually get the expression of n squared. Let's see if that is true or not. Well, it will be true, but just to get a clear idea of how it looks in reality, what we can do is we can simply say, well, what is 1? Well, 1 is just 1 square, because how many terms are there in this AP? Just one term, right? And that is clearly 1. The next is we go add 1 plus 3. 1 plus 3 is 4, and we see that that's 2 square, right? So how many terms were there in this expression? Well, n was 2, because you have the first term and the second term. So the sum was 2 square, and that clearly matches as well. Do the same, 1 plus 3 plus 5, and you will notice that that is nothing but, well, this was already 4, so 4 plus 5 would be 9. And how many terms do we have here? Well, 3 terms, 1, 2, and 3. And that clearly is 3 square, not a cube, right? So that makes the next term, well, I don't even have to do the math this time. I quite believe that this expression holds, and this should be 4 square. So So that is a very nifty little expression that we got there. It turns out that this is actually a property of odd numbers or of perfect squares, whatever you want to call it, or however you want to look at it. The sum of n odd numbers actually is equal to n squared, and that will always work out. So now that that's sorted out, I really urge you to figure out what the sum of n even numbers would be. Okay, and what I would urge you to do is do not go by the whole approach we have taken. It's rather easier, or I would say more interesting, at least I found it interesting, if we actually work with this series itself. Or what I mean by that is if we actually work with this expression itself. So let's try that. Now, if this is the sum of odd numbers, right, the sum of n even numbers would look like, well, let's start from 0. 0 is the first even number. Then the next one would be 2. The next one would be 4, so on and so forth. And you do the math, the last one would be 2 to the n. Oh, 2 into n, sorry. Now, that is interesting. Why? Because if you see, every term in this expression, which is also an AP, the common difference is still 2, is just 1 less than this expression. So 0 is 1 less than 1, 2 is 1 less than 3, 4 is 1 less than 5, and if you think about it, what is this? Well, no, this is not 1 less than that, but in reality, what's happening is we have actually gone beyond the last term. And let's have a look at the last term here. Well, if you subtract 1 from this, we get 2n minus 2. That is clearly not this term, but it's actually the term preceding this. So that also holds. This is also an even number. It's just not the last even number. Had we had another term here, well, that would have been 2n plus 1, and we would have subtracted 1 to get 2n. So this also holds. Okay, it's just that the last number doesn't really fit in with the original sequence. So what have we learned from this way of writing this? Well, if this is basically 1 minus 1, 2 can be written as 3 minus 1. Okay, 4 can be written as 5 minus 1. And this last term, so this can be written as 2n minus 1, dot, 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 minus 1, minus 1. And this term would just be 2n. Okay, so you think about this. What does this expression look like? Well, this is just you add all these terms together, right? And that is 1 plus 3 plus 5 plus so on and so forth, 2n minus 1. And we're subtracting 1 from here, 1 from there, 1 from there, all the way till 1 from there. So we are subtracting actually 1 how many times? That's the question. We're subtracting 1 n times because we're subtracting 1 those many times as there are numbers in the first sequence, and there are n of them, so we are subtracting 1 n times. So we can just write n into 1. And the remaining last term is just 2n. Okay, so this turns out to be S sub n, superscript e, or the sum of first n even numbers. Okay, so what was this expression? Well, we had already found out that it was just n squared. This is minus n, and this is plus 2n. Okay, so now it's taking some shape. What can we write this as? Well, 2n minus n is just n, and you have n squared there. So you basically get n plus 1. That is what you get as a sum of first n even numbers. So for odd numbers, we have n squared, right? But for even numbers, we have n plus 1. Or n into n plus 1. So that is how you can actually use this expression that you have found out to actually get like another way to get sum of another sequence that clearly depends on these sequences. So that is how you would do this, and I hope this video made sense, and I hope it helped you to get a clearer and more in-depth understanding about arithmetic progressions and how you can use them. All the very best and have fun.